Good afternoon, students. So let us going to see what are the dynamics of the circular motion. So we are going to derive various formula required to consider a particle moving in a circular motion. Okay. So to describe the motion or to get the dynamics of the particle, we have to know what are the forces, what kind of force is acting on the particle, how its acceleration at every point of its trajectory, how its velocity changes with the time. Okay, so let us see one by one. So this is a circle, and to analyze the circular motion, I'm going to take a very shortcut way. Shortcut way in the sense that I am going to assume that we know the calculus, and with the help of the calculus, we can derive all the properties very smoothly. So let us find one by one. Okay. So first of all, I have chosen a circle and also chosen the origin at the center of the circle. I am assuming the particle is rotating anticlockwise, and at a certain moment, the coordinates of the particle here at the point P, which is given as a polar coordinate as r and theta. What is r? R is the distance from the center to the point, or from the origin to the point where the particle is momentarily taken to be considered. And these are itself the radius of the circle, because the origin is chosen at the center of the circle. And the theta is the angle which the position vector of the particle makes with the horizontal line or x-axis, say. Okay. One more thing, I am taking the y-axis along the vertical direction, obviously, because it is a perpendicular to the x-axis. Okay. Fantastic. So now we are ready. So now what we are going to do is to consider a uniform circular motion. What is the meaning of uniform circular motion? So in uniform circular motion, it tells that the speed of the particle is constant, not the velocity. Speed of the particle is constant, but the velocity is changing. So how do you know the velocity is changing? Because if I going to draw the tangent at every point on the circle, then this is the velocity which is changing, because you know you can easily see that at every point, say A, B, C, the direction of the velocity is changing, but its magnitude, which is actually the speed, remains constant. So the acceleration, this acceleration is a particular peculiar acceleration, okay, which is generated which is generated only due to the change of direction of velocity. Not It is not generated by the change of magnitude of velocity. Okay, it is only the change of direction. Is clear? So now we are going to find the acceleration, even with the direction, even with its direction, and the force acting on the particle, which actually produce this acceleration. Good. To know this, we have to define a parameter. Parameter in the sense we have to define a characteristics of the motion, which is called the angular velocity. It has three names, But for this chapter, we have to take this name particularly, which is called the angular velocity, which is denoted by a Greek letter that is omega. Okay. Omega is if the definition is omega is the rate of change of angle or the change of angle per unit time. As simple as that. And it is denoted by d theta dt because we know now the calculus. So omega is theta dt, where the theta is in radian, not in degree. Fantastic. So we have already defined a new parameter. This new parameter is called the omega, and which is actually needed to consider the particular motion. In uniform circular motion, the omega is constant. Okay. So fantastic. So from this, if omega is equal to d theta dt, and that is dt, and we can, if omega is constant, we can easily write after. So first of all, we have to multiply the both side with dt, and that is d theta, that is omega dt. Okay. So if the angle. So if I integrate that both side with a constant c, so it becomes theta equal to omega t plus c. So I have assumed the particle starts from the rest. So that means or at t equal to 0, okay, at t equal to 0, is theta is taken to be 0. So that means c equal to 0. So theta is equal to omega t. Okay. So theta is equal to now the omega t. So we have already found the theta in terms of omega, which is constant because we are considering the uniform circular motion. So now our task is to write the position vector. Position vector, how can I write the position vector? We know because the coordinate of the P can be found dropping the perpendicular on the x-axis and y-axis. So the same coordinate r theta can be written as x and y, where this part is x and this is y. And we know from the vector chapter that the position vector of the particle is given by x I cap and y j cap. I am going to draw the picture again here so that you can easily write what is what is actually going on here. So if this is theta, then and it is x and it is y, then obviously x is r cos theta and y is r sin theta. So and theta we have already found theta is omega t. So first I am going to replace x and y by r cos theta and r sin theta. Then I am going to rewrite the theta or express the theta as omega t. So r becomes the position vector becomes r cos omega t I cap plus r sin omega t j cap. Is okay? I think it is now clear that we have found the position vector of the particle moving in a circular orbit with uniform speed or uniform omega. Good. Since r is the radius r is constant. So r I'm taking r common so that it becomes omega t I cos omega t I cap plus sine omega t j cap. So this is the vector r. Okay. So now we are ready. We have found r. Then the next task is to get the velocity. Velocity we can easily found from dr dt. That is the instantaneous velocity at any time. So we have to differentiate both sides with respect to t. Since the r is already a constant, I am taking r outside the derivative because it is constant. It is not participating in the derivative. And I'm going to differentiate that. And we know that is ddx cos mx equal to minus m sin mx. And ddx of sin mx is equal to m cos mx. So I'm using that fact. Here m is the omega and x is the t. So if I use that, so the first term becomes, the cos become minus omega sine omega t I cap plus it become omega cos omega t j cap. So I am taking omega outside. So it becomes omega r minus sine omega t I cap plus cos omega t j cap. So this is the velocity of the particle. We have found the velocity. So there is a formula of the velocity of the particle. Good. So our first purpose is now completed. So we have found the velocity of the particle. Second, acceleration. So again we have to differentiate that dv dt to get the acceleration. And we know again since the omega is constant, r is constant, so they are not taking part in the differentiation. So I am keeping them outside of ddt. And next again I am going to write ddt is minus sine omega t I cap plus cos omega t j cap. Okay. So again I'm going to differentiate that omega r. So sine omega t becomes cos with the omega out, with one omega outside. So it becomes sine become cos and one omega outside. So I'm writing omega first here, then cos omega t. Again I'm using the derivative of sine mx and cos mx. Okay. So here again, so and again the cos becomes the sine, so that is minus omega sine omega t j cap. And now since the both terms contains omega, so again I can take omega, even the minus omega, I can take minus omega common. So it becomes minus omega square r, okay, into cos omega t I cap plus sine omega t j cap. So this is acceleration. We have found the acceleration. But surprisingly, we have seen a very important thing here. Important thing, this part, there's r into this, is actually the position vector r, right? This is a position vector r. So if I put here the vector r, it is itself the position vector r. So vector A becomes a very small formula that is omega square. So this is the acceleration of the particle. So we have done almost. We have found the acceleration of the particle. We have found the velocity of the particle. So let us analyze this. Let us analyze them from the picture. So what is going on really? So when a particle is moving in a circular path, and this is the position vector, its acceleration when it is a uniform circular motion, obviously, we are only considering here the uniform circular motion, the acceleration is contains a negative sign and it is negative of the r vector. That means it is actually the acceleration is opposite to the r vector, right? because of the vector property. So that means this equation says that A is pointing towards the center of the circle. Is okay? And that is why this acceleration is called centripetal acceleration. Okay. So if the particle has is revolving around this circular orbit with uniform speed, so it actually has this acceleration which is pointing towards the center and which is called the centripetal acceleration. And what is the formula of the centripetal acceleration? We have already found that is minus omega square r. Okay, done. What is the instantaneous velocity of the particle? Instantaneous velocity of the particle is omega r minus cos, sorry, minus sine omega t. Just what we have already found, I am writing here again. So sine omega t I cap plus cos omega t j cap. Good. So if I going to take the dot product between the r vector and vector v, that is the position vector and it corresponding the velocity, we will see a very important thing. So let us do this. So I'm going to write the r vector first. So it is r cos omega t I cap plus sine omega t j cap dot. Now I'm writing the velocity vector omega r minus sine omega t I cap plus cos omega t j cap. So now using the general method of dot product, we can easily find that I cap and I cap survives, j cap and j cap will survive. So only other terms are zero because I dot j and j dot I is zero. So I can easily write that is omega r square. It is cos omega t, it is minus cos omega t sine omega t plus sine omega t cos omega t. But both terms are same with opposite sign. So they will cancel each other. So it becomes zero. Okay. So what does it mean? It means that any time this dot product is zero because I have not considered a particular time. At any time it zero. That means the velocity of the particle at any instant of time is perpendicular to vector r. That so only one way to get this, that if the particle is moving along this direction, is instantaneous velocity must be perpendicular to the r vector, right? That means the velocity must be along this direction, which is tangential. So we have proved here, explicitly proved here, that the velocity, so we have proved this relation r dot v equal to 0 actually proves that for a circular motion, no, not any circular motion, I should be precise here, for a uniform circular motion, at any instant, the velocity is tangential. So, at which we have already read in our class 10 in ICSE board for the circular motion that all at any instant the velocity is always tangent to the uh, circle and in a uniform circular motion, and it is proved today mathematically. Okay. And one more thing we have to do, and then we will actually going to the end of this particular topic. So we have to find one more thing. That is, we have to take a cross product. So I'm going to take, we have already taken, that is the right side is x-axis and this is y-axis. So if it is y, x and y, then the z-axis is vertically upward to the plane where I'm drawing it, right? Vertically upward. So this is the z-axis, which is vertically upward to the plane. So this is z-axis. Good. So this is the unit vector, say k cap, which is known already. So what I'm going to do is I'm going to take a cross product between the vector k and vector r. So with some purpose, obviously it has some purpose. So let us see what will be happen. So k cap cross r cos omega t I cap plus sin omega t j cap is okay. So if now I'm going to take a cross product here, and if I use the circular rule, cyclic rule, right? Then I can see that k cross I, there is a k cross I is equal to j. Okay, so I'm going to write that. So r cos, that is k cross I cap plus sin omega t, it is k cross j cap, right? So now I'm going to use the cyclic rule. So k cross I is actually j cap. Good. And k cross j, that I'm going opposite, that means it carries a negative sign. So it becomes minus I, the sine omega t minus I cap. So its formula becomes, I can write easily, so r minus sine omega t I cap plus cos omega t j cap. What I'm writing, just I'm rearranging those terms to express a particular quantity which is already known. Can you recognize this particular thing, that we have already found this particular thing where we have found this particular expression in the expression of the velocity. In the velocity, we have found that omega r minus sine omega t I cap plus cos omega t j cap, right? So we can easily see these bracketed expressions. We have already found the bracketed expressions which is present in the velocity. So now I'm going to multiply the upper equation, the above equation, both sides by omega. So it becomes omega k cross r becomes omega r minus sine omega t I cap plus cos omega t j cap. Now what I'm going to do? I'm going to write omega k cap as the omega vector. It is the first time I'm writing a omega vector in this topic. Before, there is no such thing we have defined. It is a first time I'm going to write the omega vector, right? So, and the right side, I can easily write it as a velocity vector, right? So there is velocity vector. So we have found the omega vector cross r vector equal to v vector. So what does it mean? It means if I am going to define a angular velocity vector as omega into k cap, then we can relate the velocity, instantaneous velocity, to the angular velocity by this relation. This is very, very important relation in circular motion. That is omega cross r equal to v. So now we are going to summarize all the picture. So we are done with, so let us going to summarize. So first we have considered a circular motion. and uniform circular motion. And at any instant, we have already seen the part, we have already found the uh, position vector, that is r cos omega t I cap plus sine omega t j cap. Second, we have found the at any instant, if the velocity is v, then the v is always the tangential, right? To the tangential, because only the tangent is perpendicular to the velocity, sorry, position. Okay, so fantastic. So r dot v equal to 0. And we have found if the circular motion happens in xy plane, then the angular velocity vector omega, omega vector must be perpendicular to the plane. That means it is along the z axis, omega into omega k. And omega r and v are related by the equation as v equal to omega cross r. The vital point is this: when it is moving, the velocity is changing because of its direction, only because of its direction, and the acceleration actually is pointing towards the center. And this particular acceleration is called the centripetal acceleration. Good. So now if I consider all the things, all the magnitudes of those vector quantities, then we are actually very important. We are getting a very important quantity, a very important characteristics. So since it is very easy to see that the omega is along z axis, so omega is along z axis. So and r is on xy plane. So the angle between omega and r is lying on xy plane, and omega is along z-axis, that is perpendicular to the r. So the angle between omega and r is 90 degree. So the magnitude of the v is the magnitude of the cross product. That means magnitude of omega r sine 90 degree. So sine 90 degree is one simple omega r. So I'm writing the magnitude of the v as simple v. So v is equal to omega r. It's okay. And if I consider the magnitude of the acceleration, so that is magnitude of the acceleration is mod of that, so mod of omega square r. So that is minus omega square r. And if I replace the omega using, okay, so if I write the omega from here, that is v by r, and put it here, then we will find it becomes v square by r. So finally, we get all the magnitudes. We get the magnitudes, okay. And which is this? First of all, the velocity is omega r, and the centripetal acceleration has a magnitude omega square r or v square by r. Okay, so this is the final expression. So we are now done with the circular motions, uniform circular motions. We have found all the things properly, and we are going to see now what is the definition of the torque in circular motions. So or in rotating motions. So suppose it is a fixed point O, and we have already studied torque in class 10 in ICSE board. The same thing is happening here, but now we have to express the torque in terms of the vector quantity. So it is a fixed point, and this is a position vector R. Position of what? Position of the force, not of the particle. A force is acting here, particular, right? So R cross F, the torque is given by tau vector is given by R cross F. Is the definition of the torque. The same definition what we have already studied in class 10, but it is expressed slightly different way. Now it is expressed that the tau is a cross product between the R position vector of the force, and the force itself. In rotating motion or circular motion, we define a new quantity beside the torque, which is known as angular momentum. So angular momentum is defined if the linear. So again, this is now again we are considering a particular origin, and now we are considering the position of the particle, not of the force. So position of the particle, and it is moving along this direction, say, with a velocity v. If the particle has mass m, so the momentum at this moment is along the velocity, and which is given by vector p equal to mv, right? We have already known that there is a definition of the momentum. So angular momentum about O with respect to O is given by R cross the linear momentum or R cross P. So when a particle is moving with a velocity or with a momentum, we can define a new quantity which is called the angular momentum. Okay. And now we are going to relate the angular momentum to the torque, and that is very, very important. So let us going to relate them. So if I differentiate dl dt, then it becomes dr dt. So I'm going to use the UV rule. So first I'm going to differentiate R, leaving P intact, and then I am putting the plus sign as default and keeping the R now uh, outside the differentiation and take the differentiation of the latter quantity. That is dp dt. So dr dt already V, velocity, and P, R, and dp dt from Newton's law, that is force, right? And Vp equal to is mv, and that is R cross F. And so we know that is a same vector. If I take the cross product of the same vector, it becomes zero. Right. So first term is zero, so it becomes R cross F. But what is R cross F? R cross F is tau. That is torque. So we have found the time derivative or rate of change of angular momentum. Rate of change of angular momentum, which is given by dl dt, is equal to is tau. That is torque. So torque has a now different definition, which is coming as a rate of change of angular momentum. It is similar way if I take the now I'm going to actually I have compared the two cases. One is the motion in 1D and one is circular motion. Okay. So in motion in 1D, the displacement is given by x. In circular motion, the theta is called the angular displacement. So x in the place of x, theta plays the role of displacement here. Okay. Motion in 1D, the velocity is given by v. Here we have defined a new velocity, new kind of velocity, it is called the angular velocity. In the motion in 1D, I have defined the linear momentum p, which is p equal to mv. And here we have defined a new quantity that is called the angular momentum, that is r cross p. In the motion in 1D, we have defined the force as F equal to dp dt. And in circular motion, in the place of force, a new the corresponding quantity is torque, and which is defined as dl dt. So this is the correspondence We can draw this correspondence between the motion and 1D circular motion. Okay. And besides that, we have found the centripetal acceleration. We have found the r dot v equal to 0 at any instant of time in uniform circular motion. So angular centripetal acceleration. So we have found all the things properly. Yeah. So this is a complete picture of the rotation of a particle in a uniform circular motion. And we have drawn the correspondence between the motion in 1D and circular motion. Okay. That's all for that.